So, do the halogens get less or more reactive as I go down the group? Reactivity decreases down the group. And why is that? What do all the halogens want to do? They all want to gain. So they all want to get an electron coming in here and an electron coming in here. So fluorine is better at gaining electrons than... Yeah, oh, Chloe. Why is that?
Well, it's the most electronegative. That's because its outer shell is closest to its nucleus.
The outermost shell is closest to the nucleus, and therefore he's going to be far more attracted as he comes in. This guy coming in, he's got to get through two inner shells before he sees the nucleus, whereas this one's only got one inner shell before he sees the nucleus. So fluorine is the most reactive. So the incoming electron is going to be less attracted each time. So there's various experiments you can do to prove that. You may have come across displacement reactions of metals. I imagine you come across some of the halogens as well. So if I take chlorine dissolved up in water and I reacted it with, let's say, potassium bromide dissolved up in water.
Does chlorine dissolve in water?
Yeah, it does. Yeah, that's why you get it in swimming pools. What would happen? Well, chlorine is more reactive. So he comes across the bromide ion with his electrons, happy boy. Because he's more reactive, he goes up to bromine and he grabs those electrons from him. So he becomes a chloride ion. So I make 2 potassium chloride dissolved up, and bromine gets displaced to be the element. And that's all in aqueous solution. So in theory, would I see anything happening? What colour would those two be? Those two, if you think they're like sodium chloride salt. In water they'd be colourless. Yeah, colourless. So they'd both be colourless. Chlorine dissolved in water is quite a pale, well, pale green colour. Quite difficult to see. Bromine in water is an orange colour. So I would see it go from pale green to orange. I could do this one as well. Chlorine aqueous in potassium into potassium, iodide rather. Let's change that up. 2 potassium iodides aqueous. That would give me 2 potassium chloride aqueous plus I2 aqueous. Again, chlorine is more reactive than iodine, so he does the same job. Chlorine is pale green. Iodine in water? No, it's like a purple vapour. Iodine in water is like a dark orange colour.
When we do that experiment, when we show the starch in the liquid,
so the final one that I could do is take bromine aqueous and react it with 2 potassium iodide aqueous, and I would make 2 KBr aqueous plus I2. So what would I see in this case? Bromine, we've said, is like an orange colour. Iodine in water is dark orange. So that's quite difficult to tell anything's happening. Can anybody remember what we do to solve that problem? Well, we add an organic solvent to the top. So we do the reaction in a test tube, and it goes the colour in water, and then we add a little bit of normally cyclohexane. And then this guy goes up into that layer like so. and that's how you can tell the colour. So you look at the cyclohexane, because in the colours in cyclohexane, if we just do what they're in water and in cyclohexane, chlorine is pale green in both, really. Bromine is orange in both. But iodine is orange in this one, and this is when you see the purple. He's purple in cyclohexane as well. So if I did this using cyclohexane, I'd see it go from orange to purple, and that's why I'd be able to see a difference for that one. So going back to this equation, this is a full equation. Can I simplify it in any way? Could I write an ionic equation for this?
Yes.
Good. What doesn't change?
Okay.
Potassium doesn't change because it's aqueous here and aqueous there. So for all of these, you can write ionic equations, which makes your life a lot easier. Ooh, they're not doing it that way. So plus 2 Br minus aqueous goes to 2 Cl minus aqueous plus Br2 aqueous. So you can do this for all of them, just removing the potassium. So often they'll ask in the exam for the ionic equations rather than the full equations, because it doesn't matter. If I was to do this experiment and use sodium bromide, would it matter? Or cesium? It wouldn't matter at all, because they're just spectator on them. So you just use whatever's cheapest, really. So that's it. Yeah. So that clearly shows this. And what type of reaction is this? Displacement. What happens here? What's my oxidation state of chlorine there? Zero. Yeah.
Reduction.
0 there. Yeah, it's redox. There he's -1. There he's -1, and there he's 0. But that shouldn't surprise you, because when we started, what were we talking about? Things moving, electrons. So it's got to be a redox reaction.